No one knows what is solenoid?
So it's a cylindrical coil. Yeah, it's a cylindrical coil which acts
Yes.
like a electromagnet after current is passed through it.
Yes. Very good. It is a cylindrical wire which is wound around some insulators. It's a copper wire wound around insulators, and it's connected to a battery supply or whatever supply it is. Means there is an edge here which is ending in this one. Now toroid is something like similar as a solenoid, but instead of this end here, there is an end here, but instead of that end, it will be like this, complete. So then we will connect one power supply. So this is called toroid. Means you can say infinite solenoid as a toroid or endless solenoid. Now if we see here, so in this one, current flows from here and there. So let's take this movement of charge in this direction. There can be any number here also. Same way here. So as it is moving in this direction, in this side, here, and this side here, in this direction and this direction. So I've drawn just a top view of solenoid, which looks like this. Direction of magnetic field inside the solenoid or magnet, which is moving from left to right. So solenoid is long cylindrical helix. Now, what is helix? Have you heard this word before? Helix?
No, sir.
Never? Okay, fine. So, you have not heard, but you have seen this actually. Have you observed the spring? They are in this form, right? Spring are in this form. Spring, they are in this form. Now, if you expand this spring here, it will form this shape. So, any particle moving this direction means horizontal direction as well as circular direction. So, they're moving in circular direction as well as forward, circular and forward direction. So combined effect of circular and forward direction is named as helical path or helix. Combined effect of circular pattern and forward direction. That is called helix. So it will be shaped as spring. The motion will be shaped as spring. So that is called helical path or helix. Now the solenoid is made simply like by winding CLOSELY closely. Yeah. Large number of turns of insulated copper wire over the insulator, any type of insulator, let it be like cardboard or china clay or whatever. Now in this one, when electric current pass through it, then it will produce a magnetic field as it is shown in like this side, right side of the our page, our screen. Let's name it something B. Figure B. This is figure A. Let's name it like that. So in figure B, you observe that, see, in this one, we don't have any derivation or something like that, okay? So whatever I'm explaining, you just understand, try to understand that. You don't have much derivation in this one. Here, just one formula, that's it. So this one, instead of writing, I'll just make you orally explanation. So don't sleep while I'm explaining, okay? Are you guys sleepy or tired something?
No, sir.
No, sir.
Okay. Because I know like, I can understand like only theory will make bore. Some people like theory, some like numerical. I like
No,
numerical
sir.
more.
These topics are way interesting than class 11 topics.
Oh, okay.
Get mostly sleep during the numerical, sir. Theory part
Oh,
is something interesting.
I feel sleepy in like theory part. Boring. I like numerical more.
Yeah.
Nice. Okay. So what I was explaining, yeah, about this. See, in this one, as you can see in the, figure A, when we are passing a current here, this will start behaving as a magnet. So when it behaves as a magnet, so obviously it will produce magnetic field, right? So if it will produce a magnetic field, so if we place near something, it will get attracted or repel, something will happen. Depends upon whatever part it has. Attracting ion they have or repulsive they have, charge particle, whatever. That is none of our business right now. Okay, so in this one, what is simple thing what we're doing here? We are passing a current, it produces a magnetic field around it. So till that it is connected with the power supply. Once it is disconnected, it will not be a source or of magnetic field. That means what? It is behaving as an electromagnet. So as you can see from the figure next to that is B, which we gave a name. There is a direction of magnetic field. See this direction? If I highlight this one, so this is the center portion. Okay, and this is the around portion, next portion. So in this one, inside the solenoid, there is a line of force which is almost, we can say, parallel. and they are in uniform, which is parallel along this solenoid. Are you observing that?
So,
Okay. So as I've shaded here, those are parallel lines. So which is along the solenoid. Now in this one, out of this field, it means like, see, obviously we know that magnetic field are closed. Unlike electric field are not closed. Magnetic field are closed. Now, if we take one small magnetic field here, and all the particles like this, if we consider on this side of a magnetic field, like let me write here. Let's consider some values here so that we can have some formula here. This what's with B is magnetic field 1/2 mu naught and I cos theta 1 minus cos theta 2. Now, see this theta 1, theta 2 are like a particle which is inside and outside. If I consider this particle at this point, this here, and this here, not direction, and this here x dot and x. You remember what is dot and what is x? Which is in going into the plane and out of the plane. Which magnetic field will be going into the plane and out of the plane? Don't you remember? We wrote somewhere here. X means into the plane. Dot means out of the plane.
out of the plane.
No need to write this. Anyhow, I'm going to erase this just for making you understand what is theta and all that. Okay. So if I take a point here at some angle, if I take this at some angle that is theta 1 and this particle, this one, and this particle at angle theta 2, making angle theta. So in short, what we have to do integration and all that. So this will be our maximum point, maximum limits here. So it starts from here and at here. So maximum we have theta 2 and minimum will be theta here. So like that. So we are not going to deep those things, not required. See, so we got here B equals to 1/2 mu naught and I cos theta 1 by minus cos theta 2. Now, if point is inside a long solenoid, then theta 1 will be 0 and theta 2 will be 180 degree. So both angle theta 0 and 180 means it will become like this 0 and 180. Full 180 and one is 0. No angle. Just 180 degree. So B will become mu naught n I. Am I right? 180 minus 1 minus 1 plus 1. 2 cancel, yeah. Now in this one, magnetic field at ends of solenoid. In that, if theta 1 is equals to 0 and theta 2 is 90 degree, then cos theta 1 is 1, cos theta 2 is 0. It is for last wala. And the first one, if it is theta 1 is 90 degree and theta 2 is 180 degree, then same way cos theta 1 0, cos theta 2 equals to minus 1. So minus 1 and plus minus, so it will become plus. So we'll have B equals to 1 by 2 mu naught n I. So instead of what generally what are we getting with this? We can make one graph that is magnetic field B around this side. This is the distance from one end. This is the end point, and this is another side of end point. This is the middle point. So this middle point means mu naught. What we got? Mu naught Ni. Here we got mu naught Ni by 2. This also mu naught Ni by 2. So the ends, both ends, we are getting mu naught Ni by 2. And at the middle, we are getting mu naught I. So what we are concluding here, so magnetic field at the end of the long solenoid is half. It's a half at as compared to the center. So in this one, in short, we can assume here, like if magnetic field is long, solenoid is long, then our magnetic field will be uniform, except ends. Except the end, it will be uniform. At the end, it is half. So it is not depending upon length. So from this, we can write here conclusion. Let's write conclusion, because I guess you will forget whatever I said just now. If you are not, it's good. So what I said, yeah. If a solenoid is long, field within it is uniform. It does not depend upon length and area of cross section of solenoid. It just produce uniform magnetic field. So field are parallel to the magnet solenoid. Make a note of it. Done.
Yes, sir.
Okay. What about others?
Yeah.
So I hope done. So let's go for toroid. Toroid is also a same thing. If I draw it like here, okay. So if I start from here, this one, current entering, so what I did here, instead of this stretched long wire, I connected those ends. Where is our solenoid? Yeah, those two ends I have made connection. So it is same thing. It's a long cylindrical wire connected end to end. We can say like that. So it is having some radius r from the center portion. A toroid is an endless solenoid, which is in form of ring. Now see, what is the purpose of this one? To make a uniform magnetic field in enclosed area. So it is also same way, it is some insulator or non-conducting material. Around that we are winding a wire with no, conducting material in the sense like metal, sorry, not metal. I mean to say in ring form. We want some non-conducting material. There, if you want to produce a magnetic field, it will be like solenoid way. It's a like a complete solenoid, endless solenoid. Here we can have some n turns, we can add some n numbers of turns and all that. So this one B equals to mu naught by 2 Ni by R. Because of this Ampere circuit, right? B dl by mu naught I. So dl is your 2 pi r. So from there we are getting all these values. Cyclic integral of B dl equals to mu naught I. Ampere's law. Ampere circuital law. That is not important here. This is more important part. Mu naught by 2 pi N I by R. Now, B is proportional to 1 by R as radius. So, number of turns per length of this toroid or torus equals to N equals to capital N by 2 pi R. Total number. So B equals to again mu naught Ni. Now see, for ideal case, these wires will be very tightly bound, or we can say they're they're closely spaced around it. This wires winding will be closely spaced in their external magnetic field will be zero because no net current passing. Means outside. No no net current passing through it. Around the outside. Outside layer. So whatever it is inside flowing inside only. Inside the solenoid. So don't get confused with this statement. So better don't consider it because nothing big here. So obviously common thing. So if you are getting confused with the statement, so leave it. So make it this much understanding. That is, so red is what? Endless solenoid, which is in ring form. Okay, which has endless magnetic field here. So more the magnetic field be considered when it is more tightly packed. These are more like these windings will be more. These windings will be more numbered, so it will be tightly packed here. Okay, make this complete here. We can do numericals then. Oh, it's already 40. Chemistry class is there, right? Sir is already posted, I think. Done? Okay, guys, stop here. I guess you are done. Okay, any question today? You want to know anything? Any question for this topic or this chapter? What happened? You slept or what? See, I told you. Here he will make you sleep. No sleeping.
No, sir.
Mm-hmm. चलो ठीक है. Go for a next maths class. Not
Okay,
maths, I
sir.
don't know. I think the chemistry, whatever. Check it.
Yes.
Okay, bye bye.
धन्यवाद सर.
धन्यवाद. Okay. ठीक है. चलो bye bye.